Opening the vault: why Roman concrete still matters today. The enduring legacy of Roman engineering stands in stark contrast to the crumbling infrastructure of the modern era. While contemporary reinforced concrete structures, designed with advanced computational models and synthesized materials, frequently succumb to corrosion and degradation within 50 to 100 years, the unreinforced concrete monuments of Rome, most notably the Pantheon and the marine breakwaters of the Mediterranean, have survived for 2 millennia. This review provides an exhaustive analysis of the material science, geochemistry, and engineering methodologies that underpin this exceptional durability. It synthesizes recent breakthroughs in the understanding of hot mixing technologies, the autogenous healing properties of lime clasts, and the unique pozzolanic reactions catalyzed by seawater. Furthermore, it evaluates the potential for these ancient technologies to address the current climate crisis through the development of low-carbon, self-healing cementitious materials. By deconstructing the secret recipe of volcanic ash, lime, and seawater, and juxtaposing it against the limitations of Portland cement, this document argues that the path to sustainable infrastructure lies in a geomimetic return to the principles of opus caementicium. The paradox of longevity. The history of construction materials is marked by a peculiar regression in longevity. The 20th century heralded the widespread adoption of Portland cement, a material that promised speed, predictability, and high early strength. When combined with steel reinforcement, it allowed for the creation of slender, soaring structures that defied the compressive limitations of stone and masonry. However, this technological leap introduced a fatal flaw: the corrosion of embedded steel. Modern concrete is designed as a closed system, intended to be impermeable and chemically inert. The goal is to protect the steel reinforcement from the ingress of chloride ions, oxygen, and moisture. Yet, the physical reality of the built environment is one of constant attack. Microcracking, shrinkage, and thermal expansion inevitably breach this protective barrier. Once the passivation layer on the steel is compromised, corrosion begins. The resulting rust occupies a greater volume than the original steel, generating expansive internal pressures that spall the concrete cover and compromise structural integrity. The economic and environmental consequences of this failure mode are staggering. The global cost of corrosion is estimated at over $2.5 trillion annually, a significant portion of which is attributed to infrastructure repair. In the United States alone, the American Society of Civil Engineers, ASCE, consistently grades infrastructure poorly, citing a backlog of repairs for bridges and dams that rely on this crumbling material system. The service life of a modern marine structure may be as short as 50 years, necessitating a cycle of demolition and reconstruction that is both capital and carbon intensive. In contrast to the fragility of modern reinforced concrete, the structures of Imperial Rome offer a compelling counter-narrative. The Pantheon, dedicated in roughly 128 CE by the Emperor Hadrian, though retaining the inscription of Marcus Agrippa, remains the world's largest unreinforced concrete dome. It has withstood 19 centuries of weathering, seismic activity, and neglect without the aid of steel reinforcement. Similarly, the submerged breakwaters of Roman harbors, such as those at Portus Cosanus and Caesarea Maritima, have endured aggressive marine environments that rapidly destroy modern concrete. Rather than eroding, these structures have, in many cases, gained strength over time, evolving into artificial geological formations. Pliny the Elder, writing in the 1st century CE, described this phenomenon with awe, noting that the concrete becomes a single stone mass, impregnable to the waves, and every day stronger. This durability is not an accident of survivorship, but the result of a fundamentally different engineering philosophy. Roman concrete, or opus caementitium, functions as an open system. It was engineered, whether through intuition, empiricism, or lost theoretical knowledge, to interact with its environment. The ingress of water, which spells death for modern concrete, is the lifeblood of the Roman material, fueling long-term crystallization processes that heal cracks and densify the matrix. Understanding this mechanism requires opening the vault of material science that has been sealed for centuries. The secret recipe: Geochemistry of the Empire. The secret of Roman concrete is not a single magical ingredient, but a sophisticated system of components that interact dynamically over geological timeframes. The Roman faber, builder, utilized a triadic system: volcanic ash, pozzolana, lime, and seawater, or freshwater, for architectural works. The cornerstone of Roman concrete technology is pulvis putiolanus, the volcanic ash found in the region of Pozzuoli, ancient Puteoli, on the Bay of Naples. While earlier civilizations used lime mortars, the Romans were the first to industrialize the use of reactive volcanic ash to create hydraulic concrete, material that can set and harden underwater. The ash from the Campi Flegrei caldera is geologically distinct. Unlike common river sands or silts, which are chemically inert, this ash is composed of glassy aluminosilicate materials formed during explosive volcanic eruptions. The rapid cooling of magma during these eruptions prevents crystallization, leaving the minerals in a highly reactive, amorphous, glassy state. Modern mineralogical analysis reveals that this ash contains zeolitized pumice and alkali-rich feldspars. When these reactive glasses come into contact with the highly alkaline environment created by lime, they dissolve, releasing silica and alumina into the pore solution. This reactivity is the engine of the pozzolanic reaction, a term derived from the very city of Pozzuoli. The Romans understood the unique value of this specific ash. Vitruvius, in his treatise De Architectura, Book 2, Chapter 6, extols the virtues of the powder found in the neighborhood of Baiae and in the country belonging to the towns round about Mount Vesuvius. He differentiates between various types of aggregates, noting that while river sand is suitable for plaster, only the pulvis from this region can produce concrete that hardens in the sea. The importance of this material drove a massive logistical operation. Ships transported thousands of tons of pulvis putiolanus from the Bay of Naples to construction sites across the Mediterranean, including the massive harbor project at Caesarea Maritima in Judea and Alexandria in Egypt. This indicates a centralized, imperial-level standardization of construction materials. The Roman engineers refused to compromise on the quality of their binder, even when local alternatives were available. The second critical component is lime. Lime is produced by calcining limestone, calcium carbonate, CaO3, in kilns at temperatures around 900 degrees Celsius to produce quicklime, calcium oxide. This process contrasts with modern cement production, which fuses limestone and clay at 1450 degrees Celsius to create clinker. The Roman process was less energy-intensive, yet it produced a highly reactive material. For decades, archaeologists and material scientists believed that the Romans fully slaked their lime, reacting it with water to form a putty of calcium hydroxide, before mixing it with the volcanic ash. This belief was rooted in modern masonry practices and a literal reading of some ancient texts. However, a landmark 2023 study by Masik et al. At MIT has fundamentally reshaped this understanding. The team investigated the ubiquitous presence of millimeter-scale white mineral inclusions, known as lime clasts, in Roman concrete. Previously dismissed as evidence of sloppy mixing or poor quality control, these clasts were revealed to be relics of a hot mixing process. In hot mixing, quicklime is added directly to the wet volcanic ash and aggregate mixture. The hydration of quicklime is highly exothermic. This reaction generates significant thermal energy, raising the temperature of the mix. This internal heat serves two critical functions: kinetic acceleration. The high temperature accelerates the dissolution of the volcanic glass and the formation of cementitious bonds, significantly reducing curing times and allowing for faster construction schedules. Chemical diversity. The elevated temperature facilitates the formation of high-temperature mineral phases that would not form at ambient temperatures, contributing to the material's unique mineralogical fingerprint. In maritime applications, seawater was not merely a passive mixing agent, but an active chemical participant. Vitruvius describes how the mixture of pulvis, lime, and rubble should be submerged to harden. Modern research confirms that the ions present in seawater, specifically sodium, potassium, and chlorides, play a vital role in the long-term crystallization of the matrix. The concrete was designed to be permeable. As seawater percolates through the massive piers and breakwaters, it does not corrode the material, as there is no steel to rust. Instead, it acts as a mineralizing fluid, carrying the necessary components to grow new crystals in the voids left by the dissolution of volcanic glass. This creates a regenerative cycle where the environment continuously reinforces the structure. Hydration chemistry and microscopic marvels. The true genius of Roman concrete lies in its hydration chemistry, the chemical reactions that transform the wet slurry into solid rock. While modern Portland cement hydrates rapidly to form a calcium silicate hydrate gel, Roman concrete initiates a complex, multi-stage geological evolution. The primary binding phase in Roman concrete is calcium aluminum silicate hydrate, CaSH. The presence of aluminum derived from the aluminosilicate-rich volcanic ash fundamentally alters the structure of the binder compared to the aluminum-poor CSH of modern cement. The CaSH gel creates an incredibly durable matrix. The aluminum ions substitute for silicon in the crystal lattice, creating a cross-linked structure that is more resistant to chemical attack and acid dissolution. This binder serves as the glue that holds the aggregates together, but it is merely the starting point for the material's evolution. One of the most astounding discoveries in the analysis of Roman marine concrete is the presence of aluminum tobermorite. Tobermorite is a rare, naturally occurring mineral usually found in hydrothermal environments where basaltic rocks react with water at high temperatures, above 150 degrees centigrade. Finding this mineral in concrete piers that cured at ambient seawater temperatures was a shock to geologists. Research utilizing synchrotron X-ray microdiffraction at Lawrence Berkeley National Laboratory revealed the mechanism. Exothermic kickstart. The heat generated by the reaction of quicklime and seawater likely raised the internal temperature of the massive concrete blocks to 85 to 97 degrees centigrade. This initial thermal spike provided the activation energy needed to nucleate Al tobermorite crystals. Long-term growth. Over the subsequent centuries, the circulation of seawater, rich in alkali ions, dissolved the residual volcanic glass and zeolite minerals, philipsite, within the matrix. This created a locally alkaline and silica-rich pore fluid, allowing Al tobermorite crystals to continue growing and propagating throughout the concrete. At the microscopic level, Al tobermorite forms platy, bladed crystals that interlock like the fibers in a piece of felt or the layers of a composite material. This microstructure provides a unique form of toughening. Unlike the brittle CSH gel of modern cement, The interlocking plates of Al tobermorite allow the concrete to absorb energy and resist fracture propagation. The crystals effectively act as micro-rebar, reinforcing the matrix at the nanometer scale. While Al tobermorite explains the durability of marine concrete, the limeclasts explain the resilience of architectural concrete like the Pantheon. The 2023 study by Masick et al. Elucidated a mechanism of autogenous healing driven by these inclusions. The hot mixing process leaves undissolved fragments of limeclasts, scattered throughout the concrete matrix. These clasts are not inert defects. They are chemical batteries waiting to be activated. The trigger? When stress causes a crack to form in the concrete, the fracture path preferentially travels through the brittle limeclasts due to their lower mechanical resistance compared to the surrounding matrix. The reaction? As rainwater or moisture infiltrates the crack, it interacts with the exposed calcium oxide or hydroxide in the limeclast. The lime dissolves, creating a calcium-saturated solution within the microenvironment of the crack. This solution then recrystallizes as calcium carbonate or reacts with local pozzolanic material to form new CaSH gel. This precipitate fills the crack, effectively gluing the material back together. Laboratory tests demonstrated that this mechanism can heal cracks up to 0.5 millimeters in width within 2 weeks. This smart material behavior explains how the Pantheon's dome, which has undoubtedly suffered cracking from centuries of thermal expansion and contraction, remains watertight and structurally sound. Engineering the Empire. Methods of construction. The material superiority of Roman concrete was maximized by sophisticated engineering and rigorous construction methodologies. The term opus caementicium refers to the composite system of masonry, mortar, and aggregate. Unlike modern concrete, which is a fluid slurry poured into forms, Roman concrete was a stiff, low-slump material, closer to what modern engineers call zero-slump concrete. The construction process was laborious and distinct from modern pouring techniques. Formwork and facing. Roman builders typically constructed permanent formwork using brick or stone, known as opus testaceum, brick-faced, or opus reticulatum, net-like stone pattern. These facing walls served as the mold for the concrete core. Aggregate placement. Large chunks of aggregate, or chimeanta, were placed by hand into the formwork. These were not small gravels, but fist-sized stones, bricks, or tiles. Mortar application. The lime and volcanic ash mortar was spread over the layer of aggregate. Compaction. Critical to the process was tamping. Workers pounded the stiff mortar into the voids between the aggregate using heavy tools. This physical compaction densified the matrix, removed air pockets, and ensured intimate contact between the reactive binder and the porous aggregate. This method is analogous to modern roller compacted concrete, or RCC, used in dam construction, known for its high density and durability. The Pantheon demonstrates the Romans' sophisticated understanding of density and load distribution. To construct a 43.3-meter unreinforced dome, engineers had to minimize the weight, dead load, of the structure as it rose in height. They achieved this through a meticulous grading of the chimeanta. As the building rises, the materials change. Foundation. Solid travertine, a heavy, dense limestone, 2,300 kilograms per meter cubed, to bear the immense load of the structure. Lower drum, a mix of travertine and tufa, providing high compressive strength but slightly lighter weight. Middle drum, tufa and broken brick, lighter still, maintaining stiffness while reducing mass. Dome base, brick fragments, strong but lighter than stone. Dome crown, Oculus. Pumice and volcanic slag, extremely lightweight, porous volcanic rocks, 600 to 800 kilograms per meter cubed, that float on water. This gradient density means the dome is heavy and stable at the bottom, but light and airy at the top, significantly reducing the hoop stress that would otherwise cause the unreinforced concrete to crack and collapse. Marine construction. The Vitruvian methods. In De Architectura, Book 5, Chapter 12, Vitruvius outlines 3 specific methods for underwater construction, demonstrating a high level of technical planning. The submerged caisson. For hard bottoms, builders constructed a double-walled wooden cofferdam, or arca. The gap between the walls was packed with clay in reed bags to create a watertight seal. Then the water was pumped out using water screws or water wheels, and the concrete was built in the dry environment of the sea floor. The poppable block, for soft or sandy bottoms. If pumping was impossible, concrete blocks were formed on the edge of the pier. These blocks were allowed to cure for at least 2 months to achieve initial strength. Once hardened, the retaining wall was removed and the massive block was tipped into the sea. The hydraulic method, the Baye method. Leveraging the unique properties of pulvis putuilano, engineers could construct formwork directly in the water. The hydraulic mortar, 2 parts ash to 1 part lime, was mixed and placed directly into the inundated molds. The mixture would set and harden underwater, a capability that astonished ancient observers and remains a benchmark for hydraulic cements today. The scale of Roman concrete construction required a vast and organized labor force. While the architects, often Greek, and military engineers provided the technical design, the execution relied on thousands of laborers, including skilled artisans and a massive population of enslaved workers. The stratification of labor was mirrored in the material. Skilled masons focused on the opus reticulatum or brick facings, ensuring the visual and geometric precision of the structure. Unskilled labor handled the mixing, hauling, and tamping of the concrete core. The repetitive nature of the layering process, placing stones, adding mortar, tamping, was ideally suited to a large, non-specialized workforce. Supply chain. The transport of volcanic ash from Pozzuoli to ports like Caesarea Maritima involved fleets of grain ships and dedicated merchant vessels, highlighting the state-level commitment to this specific material standard. Modern comparison and the sustainability equation. To evaluate the relevance of Roman concrete today, we must confront the limitations of our current dominant material, Portland cement. The cement industry is a major contributor to climate change, responsible for approximately 7 to 8% of global carbon dioxide emissions. This footprint stems from 2 sources: thermal energy. Heating the kiln to 1,450 degrees Celsius requires massive amounts of fossil fuels. Chemical decomposition. The calcination of limestone releases chemically bound CO2 directly into the atmosphere. Roman concrete production offers a nuanced comparison. Lower temperature. The calcination of lime for Roman concrete occurs at 900 degrees Celsius, requiring significantly less fuel than modern clinker production. Mix proportions. Roman mixes typically used a ratio of 1 part lime to 3 parts volcanic ash. The modern concrete often has a higher cement content relative to aggregates. LCA reality, however, a recent life cycle assessment by Martinez et al. 2025 suggests that simply adopting Roman formulations with modern technology does not automatically yield lower emissions initially. The production of quicklime is still carbon intensive. The true sustainability advantage of Roman concrete is not in its production, but in its lifespan. Amortized carbon. If a modern bridge lasts 50 years and a Roman-style bridge lasts 500 years, the carbon footprint per year of service life for the Roman structure is an order of magnitude lower. The Martinez study concluded that Roman concrete mixtures would need to outlive modern formulations by roughly 41% to break even on emissions. Given that they outlive modern structures by 2,000%, the sustainability argument is overwhelmingly positive in the long run. The economic argument for Roman-style concrete is driven by the failure of steel reinforcement. The problem: modern concrete relies on steel for tensile strength. In marine environments, chloride ions penetrate the concrete, destroying the passive layer on the steel and causing rust. This leads to spalling and structural failure within decades. The cost: in the U.S., the annual direct cost of corrosion for highway bridges is estimated at $8.3 billion, with indirect costs, traffic delays, lost productivity, running 10 times higher. The Roman solution: by utilizing a material that strengthens in the presence of seawater and heals its own cracks, Roman concrete eliminates the primary failure mechanism of modern infrastructure. While it lacks the tensile strength of reinforced concrete, it offers a superior solution for gravity structures like seawalls, retaining walls, and foundations where compressive strength is paramount. The Renaissance, Commercialization, and Future Applications. The study of Roman concrete has transitioned from archaeological curiosity to active industrial innovation. We are currently witnessing a geomimetic revolution where startups and research labs are reverse engineering ancient rocks to solve modern problems. One of the most direct commercial applications of the 2023 MIT study is the startup DMAT, founded by Admir Masek. The company has developed a product called D-Lime, which integrates the lime-clasked technology into modern concrete mixes. D-Lime mimics the hot mixing process to create widely distributed calcium reservoirs within the concrete. The material demonstrates the ability to self-heal cracks, extending the lifespan of infrastructure by up to 50% and reducing the carbon footprint by minimizing the need for maintenance and replacement. The product has already received certification in Switzerland and is being targeted for use in high-value infrastructure projects like tunnels and mines, where repair is difficult and costly. At Stanford University, geophysicist Tiziana Venorio, a native of Puzzoli, founded Flego. Her research focused on the caprock of the Campi Flegrei caldera, a natural rock that withstands immense seismic strain without fracturing. She discovered that the hydrothermal processes in the caldera create a natural concrete reinforced with microscopic fibers. Flego cement utilizes volcanic rock to grow a meshwork of intertwining fibers within the cement matrix. This provides ductility, or flexibility, to the material, a property usually lacking in concrete and requiring steel reinforcement. By emulating the natural cementation of the caldera, Flego aims to create a building material that is tough, resilient to earthquakes, and free from the corrosion risks of steel. The integration of Roman principles into modern engineering opens several strategic avenues. Coastal defense. As sea levels rise, the need for durable seawalls is critical. Roman marine concrete, with its ability to strengthen in seawater through altobermoride growth, offers a permanent solution that outperforms modern Portland cement in tidal zones. Nuclear waste storage. The mineral phases in Roman concrete, particularly altobermoride and zeolites, have high cation exchange capacities. This makes them ideal for encapsulating radioactive waste, trapping dangerous ions within their crystal lattice for geological timescales. For 2,000 years, the Pantheon has stood as a silent rebuke to the transience of modern construction. It has survived empires, wars, and the elements, protected not by steel, but by a secret recipe of volcanic ash, lime, and seawater. The recent opening of this vault by modern science, using the advanced tools of X-ray diffraction and chemical mapping, has revealed that the Roman builders were not merely lucky, they were masters of thermodynamics, utilizing hot mixing to energize their materials. They were pioneers of geomimicry, creating artificial rocks that harnessed the power of the sea to grow stronger. They engineered resilience, embedding self-healing mechanisms that allowed their structures to adapt to stress. The path forward for the modern construction industry lies in embracing these ancient principles. By shifting from a philosophy of strength through rigidity to one of durability through adaptability, and by replacing inert materials with reactive and healing ones, we can build a built environment that does not just survive the next century, but endures for the next millennium. The future of concrete, it seems, lies in its past. Architectural feats, engineering scale, and adaptability. The true genius of Roman engineering lay not just in the material itself, but in how it was applied. Roman engineers understood that concrete was weak in tension, but possessed immense compressive strength. Consequently, they developed an architectural language of arches, vaults, and domes that kept the material in compression, allowing for spans and scales previously unimaginable. Completed in AD 80 under Titus, the Colosseum is the largest amphitheater ever built. While its travertine facade is iconic, the structure is fundamentally a concrete organism sheathed in stone. Its construction required the management of materials on an industrial scale, utilizing approximately 100,000 cubic meters of travertine and an equivalent volume of concrete. The site chosen for the Colosseo was the valley of the Stagnum lake of Nero's Domus Aurea. This presented a catastrophic geotechnical risk, building a massive stone structure on soft, waterlogged alluvial deposits. The Roman solution was a concrete foundation of unprecedented size. They excavated a toroidal, donut-shaped trench 12 meters deep and filled it with a dense concrete mix using heavy basalt aggregate. This created a monolithic raft foundation that distributed the building's immense load evenly, preventing differential settlement that would have shattered the masonry arches above. Simultaneously, a sophisticated drainage system was installed 8 meters below the structure to divert groundwater and runoff, utilizing the concrete's moldability to create complex channel geometries. To maximize the height and span of the Colosseum, 48 meters high, engineers employed a rigorous zoning of materials based on density. This required a supply chain capable of sorting and directing specific rock types to specific elevations on the job site. Foundations: heavy basalt and travertine aggregate, density around 2,400 kilograms per cubic meter. Lower piers: travertine and tufa. Radial walls: concrete with brick and tufa aggregate. Upper vaults: concrete with lightweight volcanic pumice and scoria, density around 1,200 to 1,400 kilograms per cubic meter. This lightening of the load as the structure rose reduced the thrust on the lower buttresses and minimized the static load on the foundation. The use of pumice, imported likely from the same volcanic regions as the Pozzolana, highlights the integration of logistics and structural design. The Colosseum was a machine for crowd control, designed to move 50,000-plus spectators in and out rapidly. This was achieved through vomitoria, vaulted passageways that discharged people into the seating tiers, cavea. The complex geometry of these corridors, curving, inclining, and intersecting, was made possible by concrete poured onto wooden formwork. Constructing such intersecting geometries in cut stone, stereotomy, would have been prohibitively slow and expensive. Concrete allowed for the rapid replication of these complex forms, enabling the 80 entrance arches to function as a seamless circulation system. Built circa AD 110 by Apollodorus of Damascus, Trajan's Market is a complex of over 150 shops and offices that acted as a retaining structure for the Quirinal Hill, which had been excavated to make way for Trajan's Forum. It is considered one of the earliest examples of high-density urban planning. The Great Hall is a rectangular space 36 meters by 8.8 meters, covered by a series of concrete groin vaults. It represents a departure from the dark, column-filled interiors of earlier eras, allowing light to flood in through clerestory windows. For decades, architectural historians debated the structural function of the arched galleries flanking the Great Hall. Early analyses suggested these acted as flying buttresses to counter the outward thrust of the main vault, prefiguring Gothic architecture. However, modern finite element analysis by Perucchio et al. Has revealed that the concrete vault exerts significantly less lateral thrust than a masonry vault of equivalent span. The vault functions more as a rigid lid. The lateral arches provide stiffness and connectivity, but are not buttresses in the active Gothic sense. This demonstrates that Roman engineers were empirically designing for the specific properties of cured concrete, rigidity and cohesion, rather than just applying stone arch theory. The market showcases the use of brick ribs embedded within the concrete vaults. These lattice-like structures of bipedals, or 2-foot bricks, were set up first, and the concrete was poured around and over them. While initially thought to be structural reinforcement, recent scholarship suggests their primary role was constructional. Formwork reduction. The brick ribs compartmentalized the vault, allowing it to be poured in sections. This meant the wooden centering, or shuttering, did not need to support the entire wet weight of the vault at once, allowing for lighter timber structures. Guide frames. They acted as guides for the curvature of the vault, ensuring geometric consistency without requiring complex measuring for every cubic meter of pour. This technique was a response to the timber crisis of the late 1st century, where large structural timber was becoming scarce and expensive. By using brick ribs, the Romans substituted a manufactured material, brick, for a scarce natural resource, timber. Built in the late 2nd century BC, the sanctuary of Fortuna Primigenia represents one of the earliest and most spectacular applications of concrete to landscape architecture. Unlike Greek sanctuaries, which sat upon the landscape, this complex reshaped the mountain itself. The sanctuary consists of a series of 6 vast terraces rising up the slopes of Monte Genestro. These terraces were supported by gigantic concrete substructures. The use of concrete allowed for the creation of axial ramps and hemicycles that imposed geometric order on the rugged terrain. The blind corridors and barrel vaults of the substructures acted as retaining walls, holding back the hillside while providing a flat platform for the porticos above. This project demonstrated concrete's ability to act as an artificial geological force, capable of terraforming environments to suit Roman aesthetic and religious needs. Constructed between AD 308 and AD 312, the Basilica of Maxentius, or Basilica Nova, was the largest building in the Roman Forum and represents the culmination of Roman concrete vaulting technology. Structural innovation. Unlike traditional basilicas which used timber roof trusses on columns, this structure employed a massive concrete groin vault system over the central nave, flanked by barrel vaults over the aisles. The spans reached over 25 meters for the central nave and 20 meters for the side aisles. Coffering and weight reduction. The barrel vaults that survive today display deep octagonal coffers. While decorative, their primary function was structural, They reduced the dead weight of the concrete shell without compromising its stiffness, similar to the I-beam principle in modern steel. Seismic resilience. Recent surveys of the foundations reveal horizontal slip and diagonal cracking consistent with seismic activity. The fact that the North Isle vaults remain standing despite centuries of earthquakes is a testament to the monolithic rigidity of the concrete core, which, unlike masonry, does not have weak mortar joints that can easily shear. The Thermae Antoninianae, AD 212-216, represent the zenith of the Roman leisure complex. Spanning 25 hectares, the baths were not just a structural challenge, but a thermodynamic one. The Caldarium, hot room, was surmounted by a dome comparable in size to the Pantheon, approximately 35 meters span. This room was heated by a hypocaust system to temperatures likely exceeding 40 degrees Celsius with 100% humidity. The concrete shell had to withstand extreme thermal cycling, expanding when heated and contracting when cooled. A masonry dome with mortar joints would likely have developed microcracks, leading to failure over time. The monolithic nature of the concrete, combined with thick walls acting as thermal mass, allowed the structure to absorb these stresses while retaining heat efficiently. The walls contained hollow box tiles, tubuli, through which hot air from the furnaces circulated. The concrete was poured directly against these tiles, integrating the heating system into the structural load-bearing walls, an early example of building systems integration. The baths required millions of liters of water, supplied by the Aqua Antoniniana. To hold this water in concrete cisterns and pools, the Romans utilized opus signinum, or cacio pesto. This was a specialized waterproof plaster made by crushing pottery, tiles, or bricks into fine dust and mixing it with lime. The crushed ceramic acted as a pozzolan, reacting with the lime to create a dense hydraulic seal. This material was so effective that many Roman cisterns remain watertight today. Isotopic analysis of aqueduct linings shows distinct layers of opus signinum, indicating a rigorous maintenance schedule where the lining was reapplied or repaired to ensure continued operation. Roman concrete was not reserved for monuments. It was the connective tissue of the empire's infrastructure, enabling the rapid expansion of urbanization and trade. The Roman road network, spanning over 400,000 kilometers, relied on a multi-layered construction technique that functioned similarly to modern composite pavements. Concrete played a vital role in the subbase. A typical high-status road, via strata, consisted of 4 layers. Statamen, a foundation of large stones hand-placed in a trench. Rudis, a 9-inch layer of concrete, lime plus broken stone, acting as a load-bearing slab. Nucleus, a finer concrete layer made with gravel or sand to create a smooth bed. Pavimentum, the surface-wearing coarse, typically polygonal basalt or limestone blocks. The concrete layers, rudis and nucleus, provided a rigid, impermeable base that prevented the road from subsiding into the mud. This engineered rigidity reduced rolling resistance for carts and prevented the formation of ruts, directly enhancing the economic velocity of the empire. The adoption of concrete drove a fundamental shift in the Roman labor market. Ashlar masonry is labor-intensive in terms of skill. It requires trained stonecutters. Concrete is labor-intensive in terms of energy. It requires mining, hauling, and mixing. De-skilling. Concrete allowed the use of unskilled labor, slaves, soldiers, or the urban poor for the bulk of construction. A small team of skilled builders could supervise an army of laborers pouring rubble. This allowed the state to scale construction projects up rapidly in times of stability or war. Wages and social stability. Economic analysis suggests that unskilled workers received lower wages than masons, but the sheer volume of concrete projects provided consistent employment. This acted as a stabilizing force for the Roman plebs, essentially a state-sponsored jobs program. The demand for facing bricks, opus testicaeum, to contain the concrete created a massive industrial manufacturing sector. Brick stamps from the Tiber Valley are found across the Mediterranean, from North Africa to Gaul. This indicates that bricks were not just made on site, but were mass-produced in centralized factories, often owned by the imperial family, and exported. The concrete industry thus drove the development of a complex, interprovincial logistics network involving shipping, river barges, and quarry management. The lost knowledge, systemic collapse, and survivorship. The narrative that Roman concrete technology was forgotten in the Dark Ages is a simplification. It was not a collective amnesia, but a collapse of the complex economic and logistical systems required to produce it. The magic ingredient, pulvis puteolanis, is geographically specific to the Bay of Naples. To build high-quality hydraulic concrete in Rome or Caesarea, one needed to ship tons of this ash. When the political and economic unity of the Western Mediterranean fractured in the 5th and 6th centuries due to the Gothic Wars, Vandal piracy, and economic contraction, the long-distance trade and heavy bulk goods like volcanic ash became economically unviable. Builders in the Middle Ages continued to make mortar using lime and local sand, but without the specific pozzolanic ash, the resulting material lacked the hydraulic properties and extreme durability of the imperial era. They didn't forget the recipe, they lost the grocery store. The technique of hot mixing, using quicklime, was likely a trade secret passed down through guilds rather than codified in widely distributed texts. Handling quicklime is dangerous. It can cause chemical burns and blindness. As the large state-sponsored construction projects ceased, the continuity of the master-apprentice lineages broke. The nuanced understanding of how to manage the exothermic reaction of quicklime to create self-healing plasts was lost, replaced by the safer, more manageable technique of fully slaking lime. It is crucial to acknowledge survivorship bias. We marvel at the Roman concrete that has survived for 2,000 years, but we do not see the countless tenement blocks, insulae, and harbor piers that crumbled in antiquity due to poor mixing, bad lime, or lack of maintenance. The structures that remain, the Pantheon, the Colosseum, were the most expensive, most over-engineered projects of the empire, representing the absolute apex of the technology, not the average. The logistics of dominion, artificial harbors, and the grain supply. The Roman Empire was a thalassocracy. Its survival depended on the control of the Mediterranean Sea, Mare Nostrum. However, the geography of the Mediterranean coastlines did not always cooperate with imperial ambitions. The Levant and the Italian coastlines often lacked deep, sheltered natural harbors capable of handling the massive grain freighters, naves honorariae, required to feed the capital and the legions. Hydraulic concrete allowed Roman engineers to defy geography, constructing massive artificial harbors on open, hostile coasts. The construction of Sebastos, the harbor at Caesarea Maritima in Judea, built circa 22 to 10 BC by Herod the Great, a client king of Rome, serves as the premier case study of concrete as a strategic enabler. The coastline of Judea was notoriously straight and sandy, offering no natural anchorage for the Roman fleet or the merchant marine. To integrate Judea into the Roman economy and provide a secure logistical foothold for operations in the east, Herod utilized Roman engineers and Roman materials to build a harbor that rivaled the Piraeus of Athens. The logistics of construction. The scale of the project required a massive logistical operation. Analysis of the concrete cores from the submerged ruins of Caesarea reveals that the pozzolana used was not local, but imported directly from the Bay of Naples. This implies a trans-Mediterranean supply chain, where over 24,000 cubic meters of volcanic ash were shipped 2,000 kilometers to the construction site. The caisson technique. To build the massive breakwaters in the open sea, Roman engineers employed floating caissons or barges. These were large, double-walled wooden structures constructed on land, floated into position over the seabed, and then filled with the hydraulic concrete mix. The immense weight of the concrete, densified by the reaction with seawater, caused the caissons to sink to the bottom, where the mortar set underwater, creating monolithic foundation blocks as large as 15 by 11.5 by 2 meters. Strategic outcome. The completion of Caesarea Maritima provided Rome with a reliable deep-water port in the Levant. It became the provincial capital, the headquarters of the Roman administration, and the primary base of operations for the legions during the First Jewish-Roman War, 66 to 73 AD, and the Bar Kokhba Revolt, 132 to 136 AD. Without the concrete harbor of Caesarea, the Roman logistical chain for the sieges of Jerusalem and Masada would have been significantly more tenuous, relying on beach landings or distant ports like Acre. While the provinces required harbors for control, the heart of the empire required a harbor for survival. The city of Rome, with a population exceeding 1 million, relied on the importation of hundreds of thousands of tons of grain annually from Egypt and North Africa. The natural river port at Ostia was insufficient. It was prone to silting, dangerous in winter, and too shallow for the largest grain ships. To solve this, Emperor Claudius initiated and Trajan completed the construction of Portus, a massive artificial harbor complex north of Ostia. This project involved excavating a hexagonal basin inland and connecting it to the sea via canals. The entire infrastructure, quays, moles, and the massive warehouses or horea, was built using concrete. The durability of the concrete in the brackish water was essential. Military significance. Portus was not merely a civilian facility, it was the lung of the imperial army. The Annona system fed not only the mob of Rome, but also the military units stationed in Italy and the reserves for the frontier legions. The stability of this supply chain, guaranteed by the indestructible concrete quays of Portus, prevented famine-induced unrest and ensured that the emperor maintained the political capital to wage war. Furthermore, Portus served as the base for the imperial dispatch boats and elements of the fleet, allowing for rapid communication with the provinces. In the north, the Classis Britannica, the British fleet, utilized concrete and masonry technologies to establish a network of fortified bases on both sides of the English Channel, most notably at Dubris, Dover, and Boulogne. These bases were critical for the support of the legions in Britannia, a province that required a disproportionately large military garrison. The fleet's role extended beyond warfare to logistics, transporting iron from the Weald and stone for construction. The construction of lighthouses, or ferroi, at Dover, built with layers of masonry and concrete, facilitated safe navigation for the supply convoys. The ability to build durable, all-weather ports in the tidal, storm-prone waters of the Channel was a direct application of Roman engineering prowess, integrating the island province into the continental supply system. Bridging the uncrossable, offensive mobility and hydro-engineering. Rivers were the natural defensive lines of antiquity. For most armies, a wide river like the Danube or the Rhine was a formidable barrier that could delay a campaign for months or halt it entirely. For the Roman army, equipped with concrete technology, rivers were merely engineering challenges to be overcome, converting barriers into highways for invasion. The most spectacular example of concrete facilitating offensive warfare is Trajan's bridge over the Danube, constructed between 103 and 105 AD by the architect Apollodorus of Damascus. The bridge was a prerequisite for the Second Dacian War. Trajan needed a permanent, high-capacity crossing to move legions, cavalry, and siege engines into the heart of Decebalus' kingdom. Engineering specifications. The bridge spanned 1,135 meters across the Danube at Drobeta, while the superstructure was wooden, allowing it to be burned if the enemy captured the bridgehead. The 20 piers were constructed of masonry and brick-faced concrete. The construction of these piers in a fast-flowing river was a masterpiece of hydraulic engineering. Apollodorus likely utilized cofferdams, watertight enclosures driven into the riverbed and pumped dry to pour the concrete foundations directly onto the bedrock. Alternatively, floating caissons similar to those at Caesarea may have been used. Strategic impact. The bridge fundamentally shifted the strategic balance. Prior to its construction, Roman operations were seasonally constrained by the need to use pontoon bridges or ferries, which were vulnerable to drift ice and enemy raids. Trajan's bridge allowed for a continuous, year-round flow of supplies and reinforcements. It transformed the Danube from a defensive moat for Dacia into a secure Roman supply line. The result was the total conquest of Dacia, the annexation of its gold mines, which funded the Forum of Trajan and the Pantheon, and the elimination of a major strategic threat. Roman military engineering also employed excavation and embankment to modify the hydrological landscape for tactical advantage. The construction of canals allowed the fleet to bypass dangerous sea routes or move inland to support ground troops. Fossa Drusiana, 12 BC, constructed by Nero Claudius Drusus, this canal system linked the Rhine Delta to Lake Flevo, modern Isselmeer, allowing the Roman fleet to transport troops safely into the North Sea and the Frisian lands without navigating the treacherous open ocean. This hydroengineering project was a force multiplier for the Germanic campaigns, increasing the operational range and speed of the legions. Corbulo's Canal, 47 AD. The general Corbulo ordered the digging of a canal connecting the Rhine and Meuse estuaries. This was not only a logistical artery, protecting supply ships from North Sea storms, but also a way to keep the soldiers busy and disciplined during a lull in fighting. The canal allowed for the rapid redeployment of the Classis Germanica along the frontier, acting as a lateral line of communication behind the limes. While the Italian campaigns relied on pulvis putilanus, the logistical cost of shipping volcanic ash to the northern frontiers was prohibitive. In the Rhineland, Roman military engineers discovered trass, a volcanic tuff in the Eifel region that, when ground, possessed similar hydraulic properties to the ash of Puzzuoli. This adaptation was crucial for the fortification of the Limes Germanicus. The ability to source hydraulic binder locally meant that bridges, like the Roman bridge at Trier, baths, and harbor walls along the Rhine could be built with the same durability as those in Rome, without the crippling cost of long-distance transport. This localization of material science demonstrates the adaptability of Roman military logistics. The static frontier, fortifications, preservation, and the limes. As the empire transitioned from an expansionist power to a defensive one under Hadrian and the Antonines, the role of concrete shifted from facilitating mobility to ensuring permanence. The limes, the fortified borders of the empire, stretched for thousands of kilometers. Constructing and maintaining this line required a standardized, scalable building method. Hadrian's Wall in Britain represents the apotheosis of static frontier defense. While the visible facings are often dressed stone, the core of the wall and its associated structures heavily utilized mortar and rubble infill, the precursor to concrete. The standardization of fort design along the wall was made possible by these techniques. Vindolanda, a case study in preservation and layering. The fort of Vindolanda, situated just south of the wall, offers a unique window into Roman military construction. Excavations have revealed that Roman engineers often sealed the demolition layers of previous timber forts with thick caps of clay and concrete before building new structures. This practice created anaerobic conditions that preserved the famous Vindolanda tablets, leather goods, and textiles. More importantly, the use of stone and concrete for the later forts, post-120 AD, signaled a shift in strategy. The legions were no longer an expeditionary force living in tents or timber barracks. They were a permanent garrison. The concrete foundations of the Principia, headquarters, and Praetorium, commander's house, were built to last generations, anchoring Roman power in the landscape. A legion cannot survive without food. The Horaea, granaries, were the most structurally robust buildings in any Roman fort, designed to protect the grain supply from damp, fire, and pests. Concrete was essential to their function. Suspensurae. The floors of the granaries were raised on low pillars, pilae, of stone or brick-faced concrete to create a void underneath for air circulation. Structural integrity. The walls were thick and heavily buttressed to withstand the lateral pressure of the stored grain and to provide insulation. Strategic value. The durability of these concrete-reinforced structures ensured that the frontier garrisons had a secure food reserve, capable of withstanding sieges or interruptions in supply. In the Limes Germanicus and Limes Tripolitanus, these fortified granaries allowed the army to operate in arid or hostile environments where local foraging was impossible. Offensive engineering, siege warfare, and artillery. Roman concrete was not exclusively a defensive material, it was also a tool of offensive siegecraft. The Roman approach to siege warfare was characterized by massive earth-moving and engineering projects designed to inevitable the capture of enemy strongholds. The Siege of Masada, 73 AD, serves as the ultimate example of Roman engineering dominance. Faced with a fortress on an isolated rock plateau in the Judean desert, the Legion 10X Fretensis, led by Flavius Silva, constructed a massive siege ramp. While the bulk of the ramp was earth and timber, the engineering required to stabilize a 113-meter ascent capable of bearing a siege tower and battering ram was immense. Archaeological analysis suggests the use of mortar and consolidation techniques to bind the ramp's surface and retaining walls, effectively creating a paved road into the sky. The ability to create a stable, engineered surface in a loose, shifting desert environment allowed the Romans to bring their technological advantage, the siege tower, to bear against the zealots' walls. Roman artillery, ballistae, scorpions, onagers, required stable, level platforms to fire effectively. The recoil of a large stone-throwing engine could dislodge it from loose soil, ruining its aim and rate of fire. In siege lines, Roman engineers constructed ballistae, artillery platforms. These were often leveled and consolidated with mortar or concrete to provide a rock-steady base for the machines. Firepower. At the Siege of Jerusalem, 70 AD, Josephus records ballistae firing stones weighing 1 talent, 26 kilograms, over 370 meters. The ability to construct concrete hardpoints for these weapons allowed the Romans to suppress enemy defenders on the walls and breach fortifications from a distance. the discovery of concentrations of ballista stones at Gamla and Jerusalem points to the location of these engineered firing positions. Soft power and the architecture of assimilation. The conquest of territory was only the first phase of Roman strategy. The ultimate goal was the integration of the conquered people into the empire. Concrete played a pivotal role in this soft power strategy by facilitating the rapid urbanization of the provinces. The Roman bathhouse, thermae, was the quintessential symbol of Roman culture. It was a social hub, a hygiene facility, and a display of technological superiority. The construction of large heated bathhouses was made possible by concrete technology. Vaulting. The large open spaces of the caldarium and frigidarium required vaulted ceilings that could withstand the heat and humidity. Concrete barrel vaults and groin vaults allowed for these expansive interiors without the need for cluttering columns. Hypocausts. Concrete provided the stable, heat-resistant subfloors required for the hypocaust heating systems. Diplomatic impact. In the cold, damp frontiers of Britain, Gaul, and Germany, the construction of a bathhouse was a powerful argument for the benefits of Roman rule. It demonstrated that Rome could conquer the elements themselves. Local elites were quickly seduced by these amenities, leading to a cultural assimilation that pacified the provinces more effectively than the sword. Archaeological evidence shows that bathhouses were among the first public buildings erected in new provincial towns, serving as engines of Romanization. The sheer scale of Roman concrete architecture served to intimidate. The Pantheon in Rome, with its 43-meter unreinforced concrete dome, still the largest in the world today, was a testament to imperial power. But this monumentality was replicated on a smaller scale across the empire. The massive concrete walls of the limes, the soaring arches of the aqueducts, and the solidity of the basilicas communicated a message of permanence. For a barbarian tribe living in timber huts, a Roman concrete fortress appeared indestructible, a work of giants. This architectural intimidation was a calculated psychological tactic. Recent studies on the long-term psychological effects of the limes in Germany suggest that the presence of this monumental infrastructure created lasting cultural and economic divides that persist to the modern day, influencing regional personality traits and economic development. The concrete border was not just a wall, it was a civilizational defining line. Modern replication, the green concrete revolution. In the face of the climate crisis, Roman concrete has moved from an archaeological curiosity to a subject of urgent materials science research. Several companies and research groups are actively commercializing Roman-inspired technologies. Sublime Systems, MIT spin-off. This startup utilizes an electrochemical process to produce lime at ambient temperatures, eliminating the kiln entirely. Their approach is inspired by the low-energy inputs of Roman cement, but utilizes modern electrochemistry to achieve scale. Alternative cements. Research into substituting OPC with volcanic ash up to 50% has shown that it is possible to reduce the embodied energy of concrete by 16% while maintaining structural integrity for many applications. Self-healing additives. Inspired by the lime-classed discovery, modern mix designs are now incorporating calcium sources and crystalline admixtures to replicate the autogeneous healing of Roman marine concrete. Companies like Basilisk are testing self-healing concretes that use bacteria or chemical capsules to seal cracks, a biomimetic approach analogous to the Roman chemical mechanism. The legacy of Roman concrete, Opus Caemanticum, is not merely one of survival, but of adaptation. It was a material that allowed the Roman state to overcome the limitations of geology and skilled labor, creating a built environment of unprecedented scale and complexity. In the military domain, concrete was a weapon of war. It allowed the legions to fortify faster, bridge wider rivers, and harbor larger fleets than any adversary. From the breakwaters of Caesarea Maritima that projected Roman power into the Levant, to the concrete piers of Trajan's bridge that opened the path to Dacia, the material was integral to the empire's expansion and maintenance. The loss of this technology was a consequence of the disintegration of the complex imperial supply chains that sustained it. Yet, as modern engineering faces the dual challenges of crumbling infrastructure and carbon emissions, the Roman model offers a critical path forward. By understanding the mechanisms of hot mixing, pozzolanic crystallization, and lime-clast healing, we are beginning to develop a new generation of building materials. These neo-Roman concretes may not build the skyscrapers of New York, but they could build the seawalls, harbors, and foundations of the next millennium, restoring the concept of eternity to the vocabulary of construction.